the title of this experiment is determination of heat of neutralization of acid and base. So neutralization is just a reaction between an acid and a base to form salt and water. We already know that. And heat is a form of energy. So, and usually the reaction between an acid and a base is usually exothermic, in the sense that heat is always released outside the system, that's into the surrounding. So if we have salt and water being formed, okay, then thermochemically we can have we can also show the extent or the amount of heat released, okay, which is measured in kilojoule per mole or joule per mole. This is the enthalpy, and the enthalpy is just the change in energy between the product and that of the reactant. So you can have a solution formed, after which you've added your acid and a base, so you produce a solution which is supposed to contain the salt and the water. So they are the product. So the difference in energy between that of the product and that of the reactant is what we call as enthalpy. Now, enthalpy can be negative or positive. So when it's negative, we say it is exothermic. Exothermic meaning that energy or heat is released outside the system, that's into the surrounding. But if it is endothermic, that means your value of enthalpy is positive. So that means heat is required for the reaction to progress. So meaning that heat is absorbed into the system from the surrounding. So in this case, we'll be determining the heat of neutralization of acid and base. And in this case, usually acid and base reactions are usually exothermic. So we are dealing with an exothermic reaction. And why do we have to find the enthalpy change? Now, the DH value, that is change in enthalpy, actually provides us information regards the strength of the chemical species, that's acid and base. So the strength of acid and base. So it gives us an idea of the strength of acid and base. We would not be going into that to show you some, enthalpy changes associated with certain acid and bases for you to see how the strength varies according to those acids and bases. And in this case, the acid you'll be provided is hydrochloric acid, which is a very strong acid, and a very strong base. Okay, so we'll be determining the enthalpy change or the heat of neutralization of these two reactants, acid and base, to give salt and water. And you know already that if these two react, we're going to have sodium chloride plus water. All right, and you can check, you can balance it yourself. If it's balanced, okay. Now let's proceed to how do we quantify the heat of neutralization. Mathematically, how do we express it? Quantity of heat released or absorbed by a system is equivalent to mc theta. Okay, this is equal to, this is the mass, this is the specific heat capacity, the heat required to raise the temperature of a body by 1 Kelvin or 1 degree Celsius. And then we have the temperature change between the reactant product or the system, or whichever it is being considered. So we have the quantity of heat to be given by this formula. Now, Q is quantity of heat released or absorbed. This is what Q is. Then we have C, like I said, is the specific heat capacity, SHC. Okay, in our own case, the specific capacity of the solution will be required, because once you've added the acid and base, you produce in the solution. So we are assuming that the solution has same specific capacity to that of water. So that means specific capacity of the solution, if it could be CS, if we denote that by CS, okay. So we're going to have the specific capacity of water, which is 4.2 joule per gram degree Celsius, that of water, for dilute solution, because we're making a solution of acid and base, mixing them together. So in order to quantify the specific capacity of solution, considering it to be related to that of water, and that's the specific capacity of solution. And we also have to have a system where we're going to introduce our acid and base. And in this case, we'll be making use of a beaker that is going to serve as our system or a container. and we are liking that the beaker is made of glass, so we're going to have specific capacity of let's say the container or the glass or the beaker. So we're going to have that, and in this case we are going to liken the specific capacity of the beaker or the container to that of glass because it is made of glass. Then that value is a constant too, it is 0.756. So these are the constants we'll be deriving, we are going to be employing in this particular experiment. So let's try to open this up for you to understand. So since we've been able to establish Q equals to mc theta, and in our own case, this process is, of course, yeah, it is exothermic. It's an exothermic reaction. We already know that. So now we are looking at the quantity of heat released by the reactant. That is what this is going to be. What quantity of heat is released or was released by the acid and the base. And that is the heat of neutralization. And that is our Q. So Q is the quantity of heat released by the acid and base. The quantity of heat released by the addition of the acid and base, which we are going to do, this is essentially the heat of neutralization. This quantity of heat released by the acid and base is the heat of neutralization. The system in this case is going to be our beaker. So if we have our beaker like this, and then we'll have acid and base, okay, we want to know essentially what quantity of heat is going to be released when acid and base has been added, and this is what it is. So now the quantity of heat absorbed by the solution, we're going to record that, we're going to find that out, and the quantity of heat absorbed by the system is this beaker itself, okay, and that's why we are actually looking at the specific capacity of the glass, which is likely to glass because the beaker is made of glass. And then we're going to be likening the specific capacity of the acid and base to that of water being a dilute solution. So, and that of water is 4.2, okay, and this is specific capacity of the glass has to be taken into consideration is 0.756. So this is essentially what this experiment is all about, determining the quantity of heat that is going to be released when the acid and base has been mixed together with the aid of a thermometer. So we now apply this formula to find the heat of neutralization. The same way, we're going to have the quantity of heat released by A and B. Let's symbolize that with Q, which is also our heat of neutralization. So it's going to be equal to quantity of heat absorbed by the solution. By the solution is the acid and base, right? So what is quantity of heat? Quantity of heat is expressed as mc theta. It has to do with the mass, the specific capacity, and the temperature change. Okay, temperature change, final temperature minus initial temperature. So we're going to have, for this alone, for the solution alone, I'm going to be saying the mass of the solution, okay, which is m, then the specific capacity of the solution, all right, which is going to be likely to that of a dilute solution, which is that of water, assuming it is equal to that of water, which is 4.2. So that is what this value is. Then times temperature change. Okay, we're going to have a temperature change. Okay, then we'll add plus quantity of heat absorbed by the system. The system is a beaker. So in a nutshell, we're also going to find the mass of the beaker itself. All right, then we'll have the specific capacity of the beaker, all right, made of glass. So we'll be likening the specific capacity to that of glass, which is 0.756. So we'll multiply the temperature change again. Okay, so what is our temperature change? Initially, before you get to know this is the solution, remember we have acid and base. So we're going to find the temperature change, okay, the initial temperature, all right, before we added the solutions together. So in the first step, you're going to have the acid. You measure a given volume of acid in a beaker, okay, hydrochloric acid, a measured volume, and we know the concentration already. We've introduced it into the system, which is our beaker. All we're going to do is to insert a thermometer inside, all right, and try to record the temperature. And for us to know the temperature, the initial temperature of the hydrochloric acid, so it has to be where the temperature remained constant for a while, okay, that will be our initial temperature. So we're going to record that as Ti, all right. Then the same thing we are going to do under the same condition for sodium hydroxide. We'll measure a given volume, of given concentration again into a different beaker this time around. Do the same thing, insert the thermometer, try to record the initial temperature where it's actually steady, and it's expected that the temperatures of the initial temperature of sodium hydroxide should be equal to the initial temperature of the hydrochloric acid under standard conditions, so they are supposed to be equal. All right, the initial temperature of HCl, all right, should be equal to that of the sodium hydroxide. Both temperatures are supposed to be the same. So now these temperatures are going to serve as Ti. Let's say, for example, the initial temperature we found it to be, let's say Ti is 32 degrees Celsius. All right. Now this Ti is the initial temperatures of the individual chemical species separately. Now after finding the initial temperature, now after recording their temperature separately, now you're going to introduce the acid into the base. You're going to start stirring with the thermometer still inside. Okay, once that is done, you record the temperature at which the thermometer shows you that it is constant, and now that will be the temperature of the solution, because the TF, that is the final temperature, is that of the solution. Let's say it got you at, let's say, 60 degrees Celsius. Let's assuming the final temperature got you at 60 degrees Celsius after adding the acid to the base. Okay, now you're going to have TF final temperature. Your initial temperatures, we are supposed to be the same for that of the acid and that of the base. Okay, now you're going to insert it here, and for you to do that, quite easy. For you to get that, I'm going to use an example. Let's say the mass of the solution. So after you've introduced your acid into the base, you're expected to weigh to know the weight of the solution itself. So you can do that by weighing an empty beaker, then weigh the solution before you even carry out the experiment. So once you get the mass of the solution, the acid and base, let's say you got it at, let's say, 150 gram. Okay, then you're going to multiply by the specific capacity of the solution, and in this case we are assuming it's a dilute solution, of course, and we are going to assume that it's equivalent to that of water. Specific capacity of water is 4.2, so I'm going to multiply this by 4.2. Then the temperature change is final temperature minus initial temperature, so it's going to be 60 minus 32. So we're going to have 60 minus 32. I want to say something here, but before I do that, once you can check your specific capacity. If you are given a specific capacity whose unit is in Kelvin, so you have to convert these values to Kelvin. All right. If your specific capacity unit is given in degrees Celsius, then you can use this value as it is. So once we've gotten this of the solution, quantity of heat absorbed by the solution is this. So we're going to add it to that of the system, that is the beaker. So the mass of the beaker, let's say it was 100 gram. Okay, then times specific capacity of the beaker, we are assuming it is likely to be of glass, of course. So, and that is a constant 0.756 times the change in temperature. Again, you can have 60 minus 32. So once you're able to solve this, you should be able to get the heat of neutralization. Let's assume the value we got is X, so the unit should be joule per mole. Okay, if your value is too much, you can divide your value by 1000, and that means your new unit is going to be kilojoule per mole. And that is how you can actually derive or get to calculate the heat of neutralization between an acid and base, in this case hydrochloric acid and sodium hydroxide.
Finding my purpose, I don't know what makes me happy, don't know what makes me sad. I sit around and ponder.